Assalamualaikum warahmatullahi wabarakatuh and hi everyone. My name is Nuralia binti Muhammad Bakri and today I am so excited to present a fundamental topic in mathematics, which is the application of vectors in physics. Whether we realize it or not, vectors play an essential role in our daily lives, from the motion of vehicles and airplanes to how electric fields interact in our devices. Understanding vectors allows us to describe motion, forces and fields with precision, making them one of the most crucial mathematics tools in physics. In this presentation, we will explore how vectors are applied in three major areas of physics, which are mechanics, electromagnetism, and fluid dynamics. We will also go through a practical problem to see how vectors help in a real-world problem solving. By the end of this session, you will have a deeper understanding of how vectors govern the physical world and why mastering them is essential in physics and engineering. Throughout this video, we will explore the difference between vector and scalars and why this distinction is crucial in physics, how vectors are applied in three major areas of physics, which are mechanics, electromagnetism and fluid dynamics, a step-by-step mathematical problem that demonstrates how vectors help solve real-world challenges, and the broader significance of vectors in scientific and engineering advancement. So here are the list of content. Before we start, let's explore more about vectors in physics. In physics, we encounter two main types of quantities, which is scalars and vectors. Scalars are quantities that have only magnitude, such as mass, temperature, speed, and energy. They describe how much of something there is, but provide no information about its direction. Vectors, on the other hand, have both magnitude and direction. This makes them essential for accurately describing motion and forces in the physical world. Many of the fundamental laws of physics rely on vector analysis. For example, Newton's law of motion describes how forces cause changes in motion. Since force is a vector, we must consider both its magnitude and direction when analyzing motion. Next, Maxwell's equation govern electricity and magnetism and rely on vector fields to describe how electric and magnetic forces behave. Next, we have fluid dynamics equation. Fluid dynamic equations use vector fields to describe the flow of the air, water, and other fluids. Without vectors, we will not be able to accurately predict motion, analyze force, or understanding interactions in physics. Vectors are typically represented in three ways, which are graphically, component form, and polar form. Graphically, using arrows where the length represents magnitude and the arrowhead shows direction. For component form is breaking a vector into its horizontal x and vertical y components. Meanwhile, for polar form, it expresses a vector in terms of magnitude and angle. Understanding these representations allows us to break down complex problems into simpler parts. Therefore, vectors form the backbone of physics by providing a structured way to analyze motion, forces, and fields. Without vectors, we will not be able to accurately describe physical phenomena, solve equations of motion, or develop a real-world application like satellite navigation, robotics, and aerodynamics. In the following sections, we will see how vectors are applied in mechanics, electromagnetism, and fluid dynamics. Now, let's explore the applications of vectors in physics. Firstly, we have mechanics. Mechanics is the branch of physics that deals with motion and forces. Since motion and forces have both magnitude and direction, they must be analyzed using vectors. In mechanics, vectors describe quantities such as displacement, velocity, acceleration, force, and momentum, all of which play a fundamental role in determining how objects move and interact. One of the first applications of vectors in mechanics is displacement and velocity. Displacement is a vector quantity that represents an object's change in position, while velocity describes how fast and in what direction an object moves. When an object moves in 2 or 3 dimensions, we can break its velocity into components along different axes to better analyze its motion. For example, if a car is traveling northeast at 100 km per hour, we can resolve its velocity into eastward and northwards components using trigonometry. This helps us calculate how far it will travel in each direction over time. Another key concept in mechanics is acceleration, which describes the rate of change of velocity. Because acceleration has both magnitude and direction, it is a vector. This is particularly important in projectile motion, where an object follows a curved path due to the influence of gravity. By breaking the motion into horizontal and vertical components, we can determine its total displacement, velocity, and times of flight. For example, if a soccer player kicks a ball at an angle of 45 degrees with an initial speed of 20 meters per second, we can calculate how far and how high the ball will travel using vector components and kinematic equations. Vectors also play a crucial role in force analysis. Newton's second law of motion, which is F equals to ma, states that force is a vector quantity, meaning both the magnitude and direction of the force determine the object's motion. If multiple forces act on an object, we must use a vector addition to find the net force. This is particularly important in force equilibrium, where the sum of all forces acting on an object must be zero for it to remain at rest or move at a constant velocity. Engineers apply this principle when designing structures such as bridges, buildings, and cranes, ensuring they can withstand multiple forces acting on them from different directions. Another important application of vectors in mechanics is circular motion and rotational dynamics. When an object moves in a circular path, its velocity constantly changes direction. This means there must be an acceleration pointing toward the center of the circle, known as centripetal acceleration. The force responsible for this acceleration is the centripetal force, which is also a vector. Understanding these concepts allows us to analyze planetary orbits, roller coaster, and car turns on curved roads. For example, when a car moves along a curved road, friction between the tires and the road provides the necessary centripetal force to keep the car on the path. Finally, vectors are essential in momentum and impulse. Momentum, given by P equals to mv, is a vector quantity that describes an object's motion. When two objects collide, we use the principle of conservation of momentum, which states that the total momentum before and after the collision remains the same. This principle is crucial in analyzing car crashes, designing airbags, and predicting the motion of celestial bodies after impact. With this example, we can see that vectors are indispensable in mechanics. Whether we are analyzing motion, forces, or collisions, vectors help us understand and predict how objects behave. Next, we have electromagnetism. Electromagnetism is the branch of physics that studies electric and magnetic fields, their interactions, and their effects on charged particles. Vectors are essential in this field because electric and magnetic fields have both magnitude and direction. Without vectors, it would be impossible to describe how force acts on charges, how electric currents generate magnetic fields, or how electromagnetic waves propagate through space. One of the most fundamental concepts in electromagnetism is the electric field. The electric field is a vector quantity that describes the force per unit charge at a given point in space. It always has a direction pointing away from positive charges and towards negative charges. The strength and direction of the electric field at different points in space can be represented using electric field lines. The denser these lines are, the stronger the field in that region. Vectors help us determine how the electric field interacts with charged particles, influencing their motion. Closely related to the electric field is the electric force, which is also a vector quantity. The force experienced by a charged particle in an electric field depends on both the strength of the field and the charge of the particle. The directions of the force determines how the particle moves, whether it accelerates towards or away from another charge. This principle is crucial in understanding how capacitors work, as they store electric potential energy by creating an electric field between two conductive plates. In addition to electric fields, electromagnetisms also involve magnetic fields, which are produced by moving charges such as electric current in wires. A magnetic field is also a vector quantity, meaning that it has both magnitude and direction. The direction of the magnetic field around a current-carrying wire follows a predictable pattern, which can be determined using the right-hand rule. Magnetic field plays a crucial role in technologies like electromagnets, electric motors, and generators. When a charged particle moves through a magnetic field, it experiences a force that is always perpendicular to both its velocity and the field. This means that the particle does not move in a straight line, but instead follows a curved path. This principle is used in many real-world applications, such as the operation of mass spectrometers, which separates ions based on their charge and mass. Vectors also help us understand electromagnetic waves such as radio wave, microwave, visible light, and X-rays. These waves consist of oscillating electrics and magnetic fields that are perpendicular to each other and the direction in which the wave travels. These three-dimensional relationships between the fields and the wave's direction of motion is best understood using vectors. The study of electromagnetic wave is essential in communications technology as they allow for wireless transmission of data in mobile phones, radios, and satellite signals. Another important application of vectors in electromagnetism is in alternating current or AC circuits. Unlike direct current, which flows in a constant direction, AC changes direction periodically. The voltage and current in an AC circuit are represented using vectors called phasors. These vectors rotate with the time, allowing engineers to analyze how current and voltage shift relative to each other. Understanding this vectors relationship is crucial in designing power distribution system, ensuring that electricity is efficiently delivered from power plants to homes and industry. Vectors also play a role in electromagnetic induction, which is the process by which a changing magnetic field generates an electric current in a conductor. This principle is the foundation of electric generators, which convert mechanical energy into electrical energy, and transformers, which adjust voltage levels for efficient power transmission. Without vectors, it would be difficult to predict the direction and magnitude of the induced current, making it impossible to design these essential devices. Electromagnetism is a vast field with countless applications, from medical imaging, technologies like MRI scans, to the functioning of electric vehicles. All these technologies rely on a deep understanding of electric and magnetic fields, which will not be possible without vectors. By using vectors, scientists and engineers can precisely describe and manipulate electromagnetic forces leading to the advancement of modern technology. Lastly, we have fluid dynamic. Fluid dynamic is the branch of physics that studies the motion of liquid and gas. Since fluids flows in different directions with varying speeds, vectors are essential in describing how they move and interact with their surroundings. Without vectors, it will be impossible to analyze ocean currents, weather patterns, or the behavior of air around airplane wings. One of the most fundamental concepts in fluid dynamics is the velocity field. Unlike solid objects, which have a single velocity at any given time, a fluid consists of many tiny particles, each moving with its own velocity. To describe how a fluid moves as a whole, we use a velocity field, which assigns a velocity vector to each point in the fluid. This allows scientists and engineers to analyze how fluids change direction, speed up or slow down as they flow around obstacles. Another important vector quantity in fluid dynamics is pressure gradient force, which describes how pressure changes from one point to another in a fluid. Fluids naturally move from regions of high pressure to region of low pressure, and the direction of this movement is given by the pressure gradient vector. This principle is crucial in understanding weather system, as differences in atmospheric pressure drive wind patterns and storm formation. Vectors also help us analyze streamlines, which are imaginary lines that show the direction a fluid flows at a different point. If we follow the path of a single fluid particles over time, it traces out a streamline. These streamlines help us visualize fluid motion and understand how water flows in rivers, how smoke moves through the air, and how air moves over the surface of an aircraft wing. In aerodynamics, engineers use streamline analysis to design cars and airplanes that minimize air resistance and improve fuel efficiency. Another essential concept in fluid dynamics is vorticity, which describes how much a fluid rotates as it flows. Vorticity is a vector that measures the local spinning motion of a fluid. This is especially important in meteorology, where it helps predict the formation of cyclones, hurricanes, and tornadoes. In engineering, understanding vorticity allows scientists to design more efficient turbines and propellers. In addition to vorticity, vectors are used to describe circulation, which measures the overall rotation of a fluid along a cross path. Circulation is an important factor in understanding lift generation in airplane wings. When air moves over a wing, the difference in velocity between the upper and lower surface creates a net circulation, generating the lift forces that allows the plane to stay in the air. This is a direct application of vectors principle in real-world aerodynamics. Another area where vectors are essential in fluid dynamics is in drag and lift force. When an object moves through a fluid, it experiences two main forces. First one is drag, which opposes the motion and slows it down, and the second one is lift, which acts perpendicular to the direction of motion and can help an object rise. Both of these forces are vectors, meaning they have directions and magnitude. Understanding these forces allows engineers to design airplanes, submarines, and even sports equipment like racing bikes and golf balls to optimize performance. Vectors also play a role in fluid turbulence, which occurs when fluid flow becomes chaotic and unpredictable. In turbulent flow, fluid particles move in complex swirling patterns, making it difficult to predict their motion. Scientists use vector field analysis to model turbulence in wind tunnels, helping design safer buildings, bridges, and vehicles that can withstand strong winds and extreme weather conditions. From From predicting ocean currents and weather system to designing airplanes and wind turbines, fluid dynamics relies heavily on a vector analysis. Vectors allows us to describe how fluid move, how they interact with surfaces, and how forces like pressure and lift influence their behavior. Without vector, we will not be able to understand or predict the movement of air, water, or other fluids, making this one of the most crucial applications of vectors in physics. Now, let's look at the question which involved the vector calculation problem in physics. The question states that a boat is trying to cross a river that is 200 meters wide. The river flows eastward with a velocity of 3 meters per second, while the boat can move with a speed of 5 meters per second relative to the water. The water is initially pointed in a direction upstream at an angle theta to counteract the river's current. For question A, express the boat's velocity as a vector in terms of its component Vx and Vy if it is pointed at an angle theta upstream. Given that boat must travel straight across or perpendicular to the river banks, determine the correct angle theta the boat should steer. First, let's understand the boat's velocity in terms of component. Since the boat is steered at an angle theta, angle upstream, its velocity can be split into two parts. First one is Vx, which is the horizontal component, and the second one is Vy, which is the vertical component. The boat is steered at an angle theta upstream. Using trigonometry, we can express that the component as Vx equals to Vb cos theta and Vy equals to Vb sin theta. To ensure that the boat moves directly across without drifting, the boat's horizontal velocity must cancel out the river current. This means Vb cos theta equals to Vr. Substituting the given values, 5 cos theta equals to 3, cos theta equals to 3 over 5, which equals to 0.6. So, theta equals to cos inverse 0.6, which equals to 53.13 degrees. So, the boat must be pointed 53.13 degrees upstream to ensure a straight path across the river. Now that we know the angle, let's find the actual velocity component. For Vx equals to 5 cos 53.13 degrees, which equals to 5 times 0.6, which equals to 3 meters per second. For Vy equals to 5 sin 53.13 degrees, which equals to 5 times 0.8, and 5 times 0.8 equals to 4 meters per second. Thus, the velocity components of the boats are Vx equals to 3 meters per second and Vy equals to 4 meters per second. For question B, how long does it take for the boat to reach the other side of the river? The river is 200 meters wide and the boat's effective speed across the river is the vertical component Vy, which equals to 4 meters per second. So using the formula T equals to width of the river over Vy, T is equals to 200 over 4, which equals to 50 seconds. So the boat will take 50 seconds to cross the river. For question C, if the boat were pointed directly across the river without adjusting for the current, calculate where it would land downstream. If the boat is not angled upstream and simply points directly across the river, the boat's velocity components will be Vs equals to 0 meter per second and Vy equals to 5 meter per second. The river pushed the boats downstream at Vr equals to 3 meters per second. So using the formula, T equals to 200 over 5, which equals to 40 seconds. Distance drifted equals to Vr times 3. So 3 times 40 equals to 120 meters. So the boat lands 120 meters downstream. For question D, find the resultant velocity and displacement in this case. N is the result of both the reverse current and the boat's forward motion. The resultant velocity is given by V resultant equals to V at square root Vx squared plus Vy squared equals to square root 3 square plus 5 square. So the answer will be approximately 5.83 meter per second. To find direction, theta equals to tangent inverse Vy over Vx. So tangent inverse 5 over 3 equals to 59.04 degrees. So the boat moves at 5.83 meter per second at an angle of 59.04 from the shore. Now, let's find the displacement. Since the boat takes 40 seconds, we can find the displacement using the formula Vres times t. So, it equals to 5.83 times 40. 5.83 times 40 equals to 233.2 meter. So, the boat's resultant displacement is 233.2 meters in a direction of 59.04 degree from the shore. To summarize, vectors are essential in physics, particularly in mechanics, electromagnetism, and fluid dynamics. In mechanics, they help us describe motion, forces, and equilibrium. In electromagnetism, they explain how electric and magnetic fields interact. Meanwhile, in fluid dynamics, they allow us to analyze airflow, water currents, and aerodynamics. Beyond physics, vectors have numerous real-world applications. They are used in navigation systems, robotics, structural engineering, and even medical imaging technologies like MRI scans. Understanding vectors allows scientists and engineers to design safer transportation systems, predict planetary motion, and improve renewable energy technologies. Vectors are not just abstract mathematical tools. They form the foundation of modern physics and engineering. By mastering vectors, we gain the ability to solve complex problems and contribute to advancement in technology and science. That's all from me. Thank you for watching this video.